Thanks, Sarah. I just realized we're not in August at all. We're in September already. So this talk, you should be all familiar with this because you had it last month, right? What is geochron? It's a very complex branch of science, I like to say. I like what Geoscience Australia puts it as. It measures the age of Earth materials and really to try and put that into a context of other branches. In terms of, say, the minerals industry, we're mainly sitting in sort of this sort of zone of tectonics, maybe geophysics, petrology, but it can be used really as an interface to things like anthropology as well. And really, I guess what I want to demonstrate today to you is that while it's incredibly useful, if you take it out of context, if you use it, say, by itself, without really understanding the, if you like, the other three dimensions, you can abuse it and abuse it quite badly. This beautiful little spiral image going from, say, our present day, going right down all the way to the formation of Earth. It's quite a nice little depiction, and so you can see various fossil forms going through back in time. But often a lot of the things that we're doing, particularly in Western Australia, is we're sitting in the Proterozoic and into the Archean, where there really aren't any fossils. So how do we know the age of our rocks that we're dealing with? How do we know the age of different processes that make a mineralized system? And one of the real motivations, particularly for me going into the geochronology sense, is to look at a mineral systems approach. I think in the 90s, Wyborn and others, and certainly Cam McQuaig in the 2010s, really have recognized something that the petroleum guys have known for years, for decades really. And that's that models, as good as they are, trying to fit a deposit into a model really doesn't work that well. Sometimes it works, but more often than not, there's little idiosyncrasies that don't make it fit, right? And really you can boil things down into a source of fluids, pathways in which they form, the traps, and the preservation potential. And a lot of these things have timing components involved with them. And geochron in particular is very useful, say, at the global scale. And knowing that global scale window is incredibly important. But I'd say most of that sort of aspect is really limited to university sort of work. It's more the sort of province to district scale, and perhaps even into the deposit scale, where the geochron can be particularly useful in trying to delineate these four processes, particularly the latter three. Now that might sound a bit arm-waving, a bit high and mighty, but let's look at what you can actually do with them in a bit more detail. So one of the things that we do a lot is building tectonic models for a particular region, right? Sort of province scale related things. So this particular image is a cross-section of what the Triassic looked like in the New England origin in the east coast of Australia, and recognizing that there was this mantle input event at about 200 odd million years, where you had a big block of crust that delaminated from the lower lithosphere. We can look at mantle fertility through time. So this particular map is using hafnium isotopes. And if you're not familiar with hafnium isotopes, in essence, the more positive that value is, the more recently that the melt that formed that rock has been extracted from the mantle. The more negative that value is, the more in the past, if you like, it was extracted. And so you can see through time, this was made by a colleague of mine, in various time slices, jumping every 100 million years, you can see how things evolved through time. At 1600, there was a big pulse. And again, at 1400 to 1300, there was a bit of a pulse here, maybe coinciding with when Nova Bollinger sits in the Albany Fraser origin. One of the other particularly useful things is, particularly as we don't really have any fossils, is to do stratigraphic correlation. Now, we worked in chopped up terrains where they're folded. How do we know that one granite over here is the same as another granite over here, right? It's very difficult to know. We got different styles of alteration. How do we know that we're dealing with the same rock type? And so by putting a simple age on a rock enhances that confidence for mineral exploration, right? It ultimately reduces that exploration risk. We can also use it to search for the right kind of stratigraphy. So this little image here is from the Eastern Goldfields in the Kalgoorlie terrain. And your gold mineralization broadly and mainly occurred at about 2.64 billion years ago. So you want to be looking for rocks that are older than that. They're the ones that have at least some sort of potential to host gold. If you're looking for the really young stuff, the really low calcium stuff that's younger than that, well, you're not going to find any gold because those rocks weren't there when the gold came in. Right? Simple things, but very useful, very quick and easy to test them. And you can even date things in a more vein type system, you know, simpler things, really down at that sort of deposit scale. Now, it's quite difficult to date minerals directly. There's a few cases, there's a few techniques, and I see Svetlana's in the back of the room there with 3D osmium, but many things we date indirectly, right? And I'll get to that in a second. If you're not, and I think many of you are familiar with Geochron, so bear with me, but for those of you who are not, let me just give you a quick 101. Geochron is all about radioactive decay. It involves a parent isotope, this particular ion, and through radioactive decay, decays into a daughter isotope, and that can happen in one of a number of different ways. The most common of which we're interested in is alpha decay, which is essentially helium nucleus, and beta decay, which is through an electron, either through capturing it or through releasing that electron. And on this little figure on the right, you've got protons versus neutrons. And you can see this little black line that's running through the middle here, this sort of stair-stepping black spectrum. That's where your stable isotopes are. These are the guys that are happy as they are. They don't need any radioactive decay. They're happy as can be. But all these other ones want to decay. And so your red and your blue ones decay by beta decay. And as you're getting to higher and higher atomic masses into, say, your uranium series, guys, you're decaying by alpha decay. And why is that important? Well, each of these decay processes is beautifully governed by what we call half-life or a decay constant, some sort of constant rate of decay that really isn't changed by much at all. Or that you can change it through some sort of unusual cosmic ray bursts, but in the vast majority of cases, that decay constant stays the same throughout geological history. At least that's a big assumption that we have. So I've got two different decay constants, two different half-lives, if you like, very young ones. Cobalt nickel dating, and so to explain that sort of sense in a bit more, you've got your radioactive decay product, cobalt, 26 in this case, 26, no, 56. I can't quite remember the number now. Clearly, we don't use it in the minerals industry, but I'll show it to you anyway. And over 5.3 years, you're then left with half of it, right? Half of your rock is turned into your daughter isotope that is now stable. And over time, over say 5 half-lives, you're now only left with about 3% of that parent isotope, and the rest, the other 97%, is your daughter isotope. And so quite quickly, you can appreciate after 50 years, you've virtually got nothing left of that parent isotope. And to be able to do geochronology, you need both. You need at least a little bit of each. Ideally, you got 50-50. That gives you the highest level of precision if you can measure things half and half. So at these sort of time scales, 50 years, not really much use to us. In any case, cobalt, this particular isotope of cobalt is a result of essentially nuclear bomb tests, so it doesn't really occur in nature anyway. But carbon dating, very common one, carbon-14 decays to nitrogen-14. It's got a half-life of a bit over 5,000 years. And again, you can appreciate in this sense that as you get to about 50,000, maybe 60,000, maybe if you really want to push it 70,000 years, you've really got nothing left of that parent isotope, so it becomes impossible to date. But there's some interesting applications nonetheless. You can date, say, recent soil, so you can see there's a massive spike in carbon-14, not necessarily dating it, but you can actually look at the rock record and look at its chemistry, and notice that there's this massive spike in the 50s that creeps up in the 50s and the 60s, again, related to atom bomb testing. Let's say somebody gives you an old bottle of wine and says, this comes from 1780, you know, it's $3 million, please. How do you know it's that old? Well, you stick a little needle in it, you suck a bit out, and you do a bit of carbon dating, or if it's a bit younger, hydrogen dating, and you test, is that bottle actually 240 years old, or was a bottle yesterday? Right? Simple thing, you're spending $3 million, you might as well spend, you know, a couple of thousand on figuring out if it's really that old. You can use it to date groundwater and aquifer recharge, right? Again, various decay systems ranging from things that are less than 100 years old to things that are several millions of years old. Again, nothing we're particularly interested in ourselves here, but certainly for some very useful applications. We can look at human migration through time, and we can look at gorge and cave formation into the millions of years. So a nice picture of the Grand Canyon. But again, these are all very young applications. So what are we really interested in? Well, we're interested in the old stuff. And when I say old, I mean, you know, at least millions of years, right? And particularly for WA, we're looking often at the billions of years. And so there's a couple of different isotopic systems, most of which decay by alpha decay and a couple by beta. And you can see the half-lives in here range from, this is in billions of years, range from about 700 million years right up to over 100 million years, right? Enormous long periods of time. Sorry, 100 billion years, I should say. enormous long periods of time. And you might appreciate, for example, that our Earth, which is 4.5 billion years old, right? Even if you date a rock that's 4.5 billion years old, this little Sumerian neodymium system has only just scratched the surface of one half-life. Right? So precision then becomes a bit of an issue. And so you can appreciate that the uranium system and the potassium-argon system tend to have better precisions, just because there's a greater likelihood of finding, you know, an appreciable amount of parent and appreciable amount of daughter isotope in there. So what do we do to measure them? Well, these are some of the instruments we have at Curtin, and I got to say, I feel very privileged to be at Curtin, and I've been to quite a few different universities around the world, but Curtin has just about everything at your fingertips. I complain when I have to walk past Svetlana's office to the shrimp because it's, you know, 100 meters from my office, and no, I'm getting old, I'm getting tired. But most of the stuff I can just walk down the stairs. So we have a couple of different systems. We have a laser ablation inductively coupled plasma mass spectrometry that essentially uses lasers to fire into your sample that ablates that material and that gets carried away and into your mass spectrometers. You can use SIMS, of which probably the most famous one in WA is called the Shrimp, but it's a proprietary name otherwise of a SIMS machine. And we've got Chris Kirkland here allegedly showing us how to operate that machine. And that uses electrons to fire into the sample, and again, in a similar sort of way to laser ablation, bombards things off the side to try and capture those secondary ions. We can dissolve things. That's, if you're really interested in that, Svetlana's at the back here. She's the lab manager for that facility here at Curtin. That essentially uses, you can actually take individual crystals, dissolve those in various acids, and analyze the entire crystal in a whole sense. You've got an alphachron that's able to measure helium in there. You've got noble gases that are able to measure argon. And even, this is a fairly new technique, and there's some applications here, where we've got an atom probe that is able to look at crystals that are 1,000th of the width of a human hair to the atomic scale. You're able to count individual atoms. Now, because there's atoms, there's not as much volume there, so the precision is not too great, but there's some very interesting findings that you can get with there that are hidden, if you like, in all these more micro-scale applications, let's say. So what do you use? Well, the nice thing about being a Curtin and having all these at your fingertips is you've got the luxury to choose, you know, for a particular problem, the right solution. And it really boils down to three things. It boils down to precision, time, and complexity, let's say, of your crystal and what that volume is. And say most of these things are targeted towards, well, I guess uranium lead, or these laser ablation versus SIMS. But you can also have these things in the argon-argon world. So this particular plot, so this particular crystal was a standard crystal that we tried to analyze in various different machines to try and figure out what the difference in precision is. And it's a little bit small to read, particularly if you're in the back. But you can see each of these little tiny red bars. The height of those bars is the uncertainty involved in that. And so at the top, you can see ID TIMS, so TIMS. Then you've got a couple of different laser ablation methods, and you've got shrimp in the middle there. And quite quickly, you can see the height of those bars. The smaller they are, the more precise it is. And there's this little gray sort of fuzzy bar that's going across each of these little blocks. That tells you what that average uncertainty is. And if you look at the numbers there, so they're all the same age, if you like. They're all 550 something million years. The bars are all pretty much the same accuracy, but they got different precisions. TIMS gets you a precision of 0.08 million years. Super precise. If you want to know when the age of the dinosaurs died, when the age of the dinosaur extinction occurred, and you want to know that to the umpteenth detail, TIMS is the way to go. If you're not too fussed and you can deal with about 1% precision, then maybe laser ablation or shrimp is the way to go. So certainly, if you want precision, and there's some isotopic systems that you really can't do without having that high precision. This is uranium lead, but for example, if you're doing rhenium osmium, this is the only way that you can get any sort of reasonable precision that with SIMS or with laser ablation simply doesn't work. The projector will turn off in 3 minutes. That sounds like a ticking time bomb. One of the other avenues to think about is time. How long does it take to analyze your particular sample? Generally, your noble gas, so your argon-argon and your TIMS machines, if you're analyzing a representative number of crystals, a number of steps in the argon-argon world per day, you can analyze maybe half, maybe a single sample a day. Really, any more than that is you're really pushing the machine. SIMS, maybe 2 or 3 samples a day. Laser ablation, maybe 6 to 8. Right, so you can quite quickly see that that speed increases, and that's purely just the analytical time. The TIMS and the noble gas generally take longer time to actually prepare your sample as well. So there's that extra blown up time. So precision, absolutely ID TIMS. But if I want speed and throughput, I want to go laser ablation. And the final one is the complexity of it. And I've got 2 little images here. This is a kind of an image of a hole. I think this is an apatite crystal. But this particular hole, if you look at that cross section, again, a little bit blurry here, but you're going at depths of at least 10 micron. You've drilled a hole that's 10 micron deep. And in some crystals, we go down to 20, 30 micron deep. I had a project last week where we went right into the thin section glass slide, and I thought, no, this is a bit of a strange signal. All of a sudden, you're getting unusual chemistries, and I realized every spot was the same. Somebody had made a thin section slightly too thin. So I was going through into the glass. But that's very different to a SIMS analysis using the shrimp. So this is a beautiful image that Martin Danasek once took on the SEM. You can see this tiny little divot in here on this beautiful zircon crystal, and that little divot is a couple of 100 nanometers. So if you've got very complex grains, then and particularly you've got zoning in your grain, you've got to analyze things by SIMS. If you were to dissolve that grain entirely with TIMS, or if you were to analyze and ablate all the way through with laser ablation, you'd have these mixed ages, and it would be useless. So hopefully you can appreciate that there's different pros, if you like, different cons between each of the different techniques. And again, I guess a large part of it is looking at the context and figuring out what is the best technique that's going to solve the problem at hand. The other thing that's really important is this principle of closure temperature. Every mineral and every decay system are intimately linked, and they have a temperature at which, sometimes called the blocking temperature or the closure temperature, at which that crystal lattice, when it's nice and hot, that crystal lattice is nice and open. And let's say you have some radioactive decay and you get for example, a uranium ion that decays to lead. That lead daughter can then slip out of the crystal if it's hotter than 800 or so degrees, right? Out of the crystal. And if you like, that clock still hasn't started ticking because you don't even know that it's escaped out of the crystal. So you're waiting for the time when that rock cools, and cools irreversibly. So if it heats up again, you reset the clock. But it cools to the point where then that crystal of lead is stuck inside the crystal. But it depends not only on the crystal you have, but also the decay system. So if I take zircon again, you can see zircon repeats itself a couple of times in this plot. So zircon with uranium lead, because the lead ion anyways is quite large, right? It's quite a large beastie. That's at quite high temperatures. That lattice is closed enough, if you like, for that lead to be stuck. But let's say you're dealing with, well, a helium atom, for example, tiny, tiny little guy. He is only close to zircon with the uranium, thorium, helium at about 180 degrees, right? So, and again, depending on that, what you're interested in, you can use that zircon grain for multiple different applications and get potentially different ages if you have different events that are occurring. But you can see that there's a whole range of different minerals and different chronometers, and certainly this list on the left is not exhaustive, that we can use to try and if you like, solve a geochronological problem. And the other thing I'll hammer on about is context, right? Geochrono without context is absolutely meaningless. If I took this rock on the left and crushed it up, I'd have no idea what I was dating. And the reason I say this is because there is, in this particular sample, this is an automated mineral analysis image, where the oranges are kind of your feldspars here, but in essence, you've got above and below, you've got a siltstone, if you like. And within that, you've got this stratiform mineralization. And the sort of bronzy, dirty bronze looking stuff is some chalcopyrite, the bright yellow is pyrite. And within that, within both layers, you've got some titanite. And those titanites are slightly different, but not different to the point where if I crush this up and try to extract titanite by itself, I'd be able to tell the difference between. And the titanite in here is detrital. It's eroded from somewhere else. The titanite in this vein, if you like, or in this stratiform bed, has come directly at the same time as the copper gold mineralization. Right, so it's very important to contextualize that rock. Without this sort of contextualization, again, crush it up, you've got no idea what you're dealing with. But you know, sometimes life's simple. The sample on the right here has got orange plagioclase, some green hornblende, some pink quartz. It's a gabbro essentially that's been metamorphosed to amphibolite facies. And there's a little bit, if you pull it up, there's a little bit of zircon sitting within the sample, but they're not particularly big. And I can't quite read the number I've got sitting there, but even this little grain that I've highlighted is about 50, 60 micron. It's a pretty small little guys. We want spots analytical spots that are sort of, 30 odd micron in size. And when, yes, you might be able to analyze the first couple, but as you start going down this list, you might not be able to analyze them all. So then the way around it is to take, really keep in mind, you're looking at this is a thin section size photograph. You got 10 millimeters as a scale bar there. Again, this is a 1-inch round disc. You can take that block of rock that you've got, doesn't have to be particularly large, a fist-sized sample, crush it up, and you'll get a hell of a lot more zircons that are 60, 70 microns that you can then analyze. But again, sometimes you've got complexity and you really can't crush it up. So what do? Do you crush it up or do you keep it intact? Now, the beauty of, again, a lot of the instrumentation, particularly with SIMS and laser ablation, is you can keep things intact. There's a couple, certainly, like rhenium, osmium, argon, you don't have a choice. You got to crush it up, okay? So you can, if you've got some complexity, you can sort of micro drill bits out, you can be quite targeted with it. But certainly the pros of in situ work is you preserve that textual context, right? You know exactly what you're analyzing. And certainly there's less sample preparation time. You got a polished block like that, you can stick it next day into the laser ablation, no problem. When you crush it up, again, there's a couple of, you can see there's more pros in there, but I guess different pros and cons there. You can capture, say, rare minerals, like if your zircon is not abundant enough in your thin section or your polished block itself, you can grab it out of there. You can do full optical and image characterization. So, for example, like you can get a lot of zircons out here, and you can actually image them with transmitted light, something you certainly can't do in a polished block. You got other minerals hiding behind there. And so you get the option to pick what you want to pick, right? This is a plagioclase sample from a basalt, and it's got some sericite in there, and it's got some beautiful plagioclase in it. And as much as we try to separate these crystals out with gravity or magnetic separation, at the end, they got the same properties. So it's impossible to separate without somebody painstakingly picking these things on the microscope. And you might be interested in the crystallization age, in which case you go for the plagioclase, or you might be interested in the alteration age, maybe associated with some gold-bearing fluids, who knows? And so you might want to date the sericite, right? So you get the option, but these things are really only possible by doing it ex situ, you're crushing it up essentially. And for that ex situ, we kind of go through a workflow of, we get some samples, we chop it up into smallish, sort of 3-4 centimeter chunks, and that can go into a machine called the cell frag, which is like you're sticking your rocks with some water into a bath that's getting lightning bolts applied to it. You're sticking 400,000 volts worth of electricity into it. And you might ask, why? Well, what you get at the end of it is you get crystals that break along their crystal boundaries. So you can get these beautiful needle-like acicular minerals dropping out that if you tried to do this in a tungsten carbide mill, you'd just pulverize the hell out of it and you get little chunks out of it. A fantastic little machine. Sounds like there's a rave concert going on when it's on, but it's a beautiful little thing. We can then take it through a range of I guess, gravity or density separation techniques, and then through magnetic separation to concentrate what we want, pick it, mount it in, say, resin, and analyze it in whatever machine we want to analyze it, whatever that might be. And over the last couple of years, and there's been, say, decades worth of work that's gone into it, we've kind of come up with this maybe corny name called Chrono Tra, which is really a nested series of workflows which takes a rock, contextualize it, analyze it, and reports on it, right? It's this essentially, it's just knowledge that is taken, and with that analytical infrastructure that we have, you can analyze anything. And I almost guaranteed, if we can't do it at Curtin, you won't be able to do it anywhere else. Don't quote me on that, but most things we can do. We're, as Brent McInnes would like to say, a one-stop shop. And so what I really love at Curtin is not only do we have a hell of a lot of analytical equipment, they're backed by fantastically experienced technical and laboratory managers. That just means that know-how is there, right? I've been to plenty of places where you've got this beautiful equipment, silver, shiny, but no one uses it. This stuff is used day in, day out, which means it's maintained. You've got that expertise there, you've got that know-how. And that's really, if you like, an intro to Geochron. Don't worry, it's not that much longer. I'll just show you a couple of little quick case studies, and then I'll let you get back to drinks. So the first one that I'll show you, this was done maybe 2 years ago here. And this was the first study we ever did at Curtin, and one of the first in the world in using in situ rubidium strontium geochronology. And Anglo Gold Ashanti came to us. And they recognized that they had 2 gold-bearing pyrite mineralizing events. And they said, can we date this? The backstory is that they'd just given up a whole bit of tenement around the Tropicana area, and they were then retrospectively asked themselves, was that a wise move or was it not? So if you're unfamiliar with the area, we're sitting here in the southeastern part of the Albany-Fraser origin, which kind of stretches across southern WA in this sort of arc shape. And Tropicana sits almost in the northeastern corner of it, in this I guess, reddish terrain called the Plumridge terrain. It's this deformed bit of Archean Yilgarn crust that's been reworked through orogenesis along the margin of that belt. Zooming into this little spot here, we've got Tropicana with its various pits sitting in this little spot here. And around the outside, there's all these little golden yellow diamonds here are gold prospects around the area. None of them have any sort of, not quite to the economic potential of Tropicana, but they are there. There's sniffs of gold sitting around there. I guess one of the other questions for them is, why is Tropicana as endowed as it is, and why these others not? In terms of a quick geological history of Tropicana, there's really not that much that's happened. There's a lot that happened at the beginning. So you had some 2.7 billion years ago, you had some crystallization of igneous protoliths. You had your gabbros and your granites that formed. They then rapidly underwent sort of amphibolite to granulite facies metamorphism. And within that time period, either at this time period or shortly after, you had gold mineralization coming in. It's a little bit tricky to tell. And depending who you talk to, it's either this time frame or this time frame when the gold came in, but old, Archean, or Archean. And then really nothing happens. This sort of stuff doesn't really happen too much in the Plumridge terrain. And then maybe you got some sort of younger events happening there. But everything generally is focused here on the Archean. No real hints of any Proterozoic activity. Bit of a complex slide, but really what I want you to get out of it is there's two main pyrite forming events, both gold bearing, so pyrite 1 and pyrite 2. And they seem to be associated with two generations of biotite. Biotite 1 and biotite 2, for lack of a better name. You get this beautiful clean biotite 1 that seems to be recrystallized into biotite with some quartz in there. And the same sort of thing, you get some biotite 1, this darker biotite here, that seems to be a bit paler, a bit more recrystallized, a bit more altered looking. In detail, what that looks like under the SEM is, again, you get this beautiful clean biotite, and we'll zoom in of that little region. And then you get this dirty looking quartz and biotite intergrowth. And each of these little circles, by the way, are those laser ablation holes that you can see what's been capturing it. In other pits where they seem to, so here that it's kind of weakly recrystallized into that biotite 2. In one of the other pits, it seems to be far more recrystallized, and it's a bit harder to tell the exact boundaries between biotite 1 and biotite 2, but seems to be broadly associated with these titanite and rutile exsolutions. So we looked at the ages of these, and these are rubidium-strontium diagrams. So you got rubidium over, or 87 rubidium over 86 strontium on the x-axis, 87 strontium over 86 strontium on the y-axis. And if you're unfamiliar with these, the way they work is essentially, if you get a whole series of points that fall on a line, they may be isochronous. They may have formed at the same time. The steeper that line, the older it is, the shallower that line. If it's horizontal, it's an age of 0. And we recognized that there was a bit of a spread in data. Imagine these points were uncolor coded, right? You'd say, well, there's a bit of a shock on the data, Hugo. How do you make anything out of it? When you color code it, certainly by where it's from, in the clean biotites, that's just these red dots. And the almost fully recrystallized stuff, not shown in this image here, are these green dots. And there's one big green dot there. There's a couple little guys down below. But really, this sample predominantly records its first biotite. But notice how there's all these gray dots too, right? Falling off the side and getting apparently younger ages. Again, you crush this rock up, you're going to get a bit of a mixed smear of ages from about 2,500 to maybe 1,200 in there, depending on what grain or what fraction of a grain you analyze. In some of these other samples, you seem to have almost exclusively that younger event, that 1,200 million year event that you recognize. And so what we recognize is one, we have that 2,500 million year event. That seems to be the same as what everybody else has been saying in the past. But we also have that 1,200 million year event. And you might ask, well, what's the significance when it comes to gold, right? Which was more important, if either? Well, when we looked at the satellite deposits, one of the more unusual things we discovered is you only had this younger age. Now, very poor precision. Muscovite doesn't have a lot of rubidium in it. But hopefully I can convince you that despite the poor precision, that's still very much Proterozoic, right? It's not Archean. And each of the 3 satellite deposits showed the same. So then the question was, well, if this stuff didn't have gold, the implication was that the earlier Archean forming event, that was still the big driver. And these little satellite prospects with only a little hints of gold Well, they might have seen that overprinting event, that maybe that remobilization event, but was there a hell of a lot of extra gold coming in? Probably not. Again, if we take all the data from all the samples that we analyzed and plotted them all onto a single isochron, you can again see those different points. The red one certainly seemed to match with the previous geochron that's been done, and the later one doesn't seem to be particularly important for gold. And again, a little figure summarizing that all. Let me take you to another study. We've got Rowena in the room here, who I've just met 10 minutes ago, but we published a paper on last year. So it shows that you can work with anybody across the country, across the world, and do great science without knowing each other personally. I don't know what that says about me. But again, a massive team effort between Anglo-American, Mintex, and ANU. And here we're looking at stratigraphy undercover. Anglo were exploring in the south of the Mount Isa Terrane. So this is a this is a gravity and an aeromagnetic photograph, I think that way around. So Mount Isa, the inlier itself is outlined in a sort of black line that you can see going around the top here. And they've got world-class IOCG deposits, world-class lead zinc deposits. And so Anglo-Americans thought was, well, if the stuff is outcropping, surely it's also undercover. Well, sound approach. But there's a lot of cover. Like we're talking 800 meters of cover of Phanerozoic rock. So it's a lot to drill through. You get some nice Cambrian trilobites in that cover over the top. Pretty looking things. And so they drilled 7 drill holes. And the first 3 drill holes were really targeted by ANU. But then, because we're so good, we got holes 4 onwards. And very quickly, so the samples were being sent to us, we were crushing up, sending the results back within a month. So they could really determine on the fly whether they wanted to keep drilling. And what we discovered, so that 7 drills drilled various lithologies. You got some granitoids, some gneiss, some metasedimentary rocks. Most of what we dated was with zircon. So there's a nice little cross-polarized photograph of some of these zircon grains with some psychedelic colors here. But broadly, all the strata fall in this 100 million year window from 1860 odd to 1760. There's a bit of later metamorphism and some very late stage pegmatites that are about 50 million years younger. But the vast majority of this, 99% of this rock would have formed before 1750. You can even take, and you say, well, that's all great and dandy. If you knew nothing else, you could take something like hafnium isotopic data, and you could say, well, is there any relation of this part that we're looking at south of Mount Isa to the real Mount Isa? Is it really related, or is it even related to other things? And with that, you can add some hafnium isotopes as a complementary tool to kind of trace these things out. So not an age technique really, but a geochemical technique. So you can plot the age of your things on the y-axis, and on the x-axis, and on the y-axis you can have your hafnium data expressed in this epsilon notation. But again, keep in mind, positive is more juvenile, more recently mantle derived. Negative is more evolved, if you like, more. If you want to think about when it was arrived, you can kind of follow these gray lines towards this depleted mantle line, this solid black line there. But really, we're using it as a tracing tool. So I've taken these little clusters of data that we had in our southern Mount Isa terrane and put a little black outline across the top and compared it to what we know. And there's quite few data in the Mount Isa inlier, mainly because everyone did the exploration back in the 80s. And hafnium has only become a tool in the early 2000s. A little bit there, but not a lot. But despite the few data points, you'd say, well, you know what, Hugo, that's a pretty good match. That's not too bad, right? It's what else do we know about this region? Well, we know Mount Isa at some point was connected to the Gawler craton before the Thomson origin came and smashed its way through in the middle. And through all of that data cloud, you say, well, that's not a great match, Hugo. But if you kind of pull yourself back a bit, a lot of the red points in here, the yellow and the blue points, not a fantastic match, I'll admit. Possibly there's a link there to the Gawler craton as well. But what did it all mean for Anglo and their exploration? Well, they were looking for these red dots here in the east, admittedly, but there was some other lead zinc stuff happening in the west here. So they really wanted to target rocks that were in, if you like, this second and third supercycle of the Mount Isa terrane. So you had this basement called the Caledonian-Leichhardt complex. That was then overlain by the Leichhardt superbasin, and then you had the Calvert superbasin and the Isa superbasin. They were looking for these younger 2 blocks. What we were finding was this younger stuff, right? And eventually, after hole 7, they said, you know what? We're stopping shop. We're not drilling anymore. And for what was essentially $100, maybe $200,000, they could answer that question and say, you know what, we probably should have stopped a couple of holes ago, but we're going to pull up shop and move somewhere else and explore somewhere further to the east. And I'll keep my mouth shut on whether they're having success or not over east. The last little case study I'll show you is a fairly recent bit of work we've been doing with IGO. Submitted the article 5 hours ago, maybe. And again, a big curtain team, because it's a bit of an unusual case study here. A bit of certainly something new for me. Not a completely new technique, but quite different. Let me take you across the other side of the world. We're now in East Greenland, and we're sitting in the eastern East Greenland Caledonites. This is 430, 440 million year old belt, this orogenic belt that formed in response to if you like, parts of Norway and northwestern UK smashing into Greenland, and then eventually rifting apart in the opening in the Atlantic. And what IGO had was they were targeting these little copper prospects that were delineated along the belt back in the 60s, 70s, and 80s by Danish geologists mainly. They were also found in the north, but you had this potentially 1,200 million year belt of copper mineralization hosted in sedimentary rocks. So I got little 50-cent coins maybe of samples, because hey, it's heavy to carry this stuff out of Greenland, of samples along the belt to try and see, can we date that mineralization? What's it being caused by? Does that Caledonian, is it diagenetic, this mineralization? Is it driven by that Caledonian orogeny? What should we be looking for? Should we be looking close to granites that are associated with it? Should we be looking at deeper parts of the basin? What's the story there? It's a very remote area. That's the only way to get around. And no, I didn't take this photo. I wasn't there, sadly. Would have liked to go, but unfortunately, I'm stuck in an office now. They collected, say, 8 samples across this 300-kilometer belt. So it doesn't look like much on the map, but it's an enormous distance to kind of traverse through. And I got a range of different samples from there to things like, you've got this beautiful gray little chalcocite blip, quite large, almost a centimeter in diameter. That has this beautiful blue calcite zoning around the outside. And this, hard to tell, but there's some little chlorite, albite, and barite sort of just zoning and rimming their way around the outside of this thing too. You get some unusual, maybe supergene, maybe hypergene mineralization, where you get some lead sulfates. You get some various oxide minerals in there, but you get some copper and some lead minerals in there. And you get very hard to see in these images, but there is, if you take my word for it, tiny little chalcocite, little disseminated across these. Essentially, what are all siltstones of various compositions. Some a bit more clay-rich, more greenish, some a bit more quartz-rich, those sort of orangey bits. And you can even see in this sample, you have some sort of some bedding, if you like, that's running sort of in this orientation, sort of northeast to southwest in this particular section. Was there anything to date? Not really. But there was one little thing, and that's what all these pink stars are alluding to. A mineral called xenotime. You might be familiar with it, you might not be, but it's essentially some rare earth element phosphate. And it does have appreciable amounts of uranium and thorium in it, which should decay to lead, hence uranium-lead dating. But then the question was, okay, it's great on this automated mineral analysis map. Is it really truly related with the mineralization? These sort of darker grain specks that you can see here are your xenotime, and this little CC, this lighter stuff, is your chalcocite. And this is about as good as it gets, I think. This little guy is rimmed on all sides. Well, this little guy in particular is rimmed on all sides by that chalcocite. And you see that in these particular samples. I mean, in all 3 samples, you see the same. Here you've got that chalcocite again, intimately associated with that xenotime. So I thought, if we date that xenotime, we're going to get the age of mineralization. And we did. And it's quite complex because there's some lead incorporated in there. So you don't get a nice, if you know these Concordia plots, you've got your one isotopic system, essentially 207 lead with 235 uranium recast in a special way. And your other isotopic system, 238 uranium decaying to 206 lead. If they form a nice regression, you can take that lower intercept, and that's the age of that xenotime forming event, let's say. That was a bit of a problem, because in the 90s, some of the guys that looked at these chalcocite things, dissolved them, did some lead isochrons on them, and the data all looks pretty good. But what age did they get? 680 plus minus 65, a little bit imprecise, but all right. Roughly 700 million years. And that is when these rocks were deposited. So that the implication was, these were diagenetic. How can we reconcile some 700 million year lead ages with some 440 million year Xenotime ages. It seems to be a paradox, right? That seems to be in contrast. And what I hadn't realized at the time is when you look at this chalcocite and cross section, the vast majority, a good 95+% by volume, are these. And so this little panel here, if you like, the bottom, or this sort of side of the panel is this bottom section of this rock, are these really inclusion-rich bits of chalcocite sitting in here. And those inclusions are inclusions of the host siltstone, essentially. Then you get out of this little area and the inclusions drop away. You get sometimes these little corridors, if you like, that are coming through here. And that turns into this disseminated stuff on the outside. And all the dark gray stuff in here is that host siltstone. And when we looked at just the composition of that lead, what we quickly realized, well, two things. One is this stuff, the cores are way more precise. So there's a little inset, this tiny little inset here, way more precise, but they seem to all broadly overlap with each other. And the implication is that 440 million year event wasn't responsible for copper mineralization. All it did was to strip the copper locally, recrystallize the edge of these blebs, and maybe, strip a little bit of copper, strip a hell of a lot of lead away, because the lead gets a hell of a lot more imprecise, probably take some iron away too. So not a great finding. Well, in some respects. It just meant that the exploration model was, let's look at the whole belt, and let's still look at the whole belt, as opposed to let's look for something that is purely associated with Caledonian metamorphism. So to kind of summarize this little case study is there are these two horizons, and really we only focused on one horizon, where you had this diagenetic chalcocite that formed within the siltstone, and that's when most of your copper came in. But what you might notice is these bronzy colored stars here, and these are your chalcopyrite rich horizons. That's future work. I think the team has just got back from recent fieldwork in Greenland. So hopefully we can kind of uncover this mystery a little bit more, as what's going on with maybe some supergene or hypergene alteration. But really, this 440 million year event, you got some granitoids coming in, you get everything that gets folded and chopped to pieces, isn't doing a hell of a lot for your copper mineralization. My last slide, some of the other things that we've been doing, and there's a couple of people in the room here that are involved in some of these. We, by sheer luck, discovered the oldest magmatic nickel copper deposit in the world. It's about 100 million years older than the next oldest, which is in Finland somewhere. Called the Andover nickel copper deposit or intrusion sitting up in the Pilbara, pretty close to Karratha. And Josh Coombs is in the back here if you want to chat to him. I won't say any more. But very interesting rocks that we've got here, very interesting units in there. We've done things looking for South 32, looking at their coal basins in New South Wales. And they had these sills and these coal seams, if you like, and some of them were really cooked and some of them were not cooked. And I thought, hey, well, maybe some of these coal seams, these igneous intrusions came in before the coal seam was even deposited, ergo not cooked, whereas then a sill comes in later, cooks everything else. Certainly two different lithologies, and the simple thing was, hey, they're probably two different ages. Turns out they're not. 200-ish and 200-ish as well, the green dots and the blue dots. Same age, we didn't solve their problem. All we could tell is there's something else going on in the picture, not two different ages. So back to the drawing board. We helped sort of uncover some sort of hidden suture zones with MOHO resources sitting in between the Mount Isa Terrane and the Georgetown Terrane. It's bloody chopped up in that area. There's probably loads of microcontinents squashed in between there. And they were looking at some unusual gold, silver, lead, zinc mineralization, unusually polymetallic, probably a couple of different events there, difficult to constrain. Sitting right at the edge of the Georgetown inlier. And as these things have, suture zones are often geologically or rheologically weak zones that now have a nice little basin sitting over the top. So while they're possibly some of the most exciting things to look at, because they're tapping a direct mantle to crust corridor, they're some of the hardest to access. And so moving undercover and exploration, that's certainly one of the ways forward. And I think in the next couple of decades, there's going to be some big deposits made along these undercover regions, along suture zones. And then a bit of a larger projects, individual projects that will probably coalesce into one, working with Anglo Gold Ashanti. So I thought Jenny was sitting somewhere in the back there, with Dacian and with Regis, looking at the stratigraphy of that eastern Laverton belt and western Birdville terrain to try and kind of uncover the complexities that we've got in the belt there, because everything's chopped to pieces, outcrop's pretty poor. So to try and figure out what's going on there needs some detailed geochronology, and there's still work being done there. I'll leave it at that. Hopefully I've maybe not convinced you, but at least enlightened you of that Geochron is incredibly useful, but very importantly, it underpins other geoscience. It is not a technique to be used in isolation. It's a technique that's to be used contextualized. It's adding that fourth dimension to 3D geological models. There's an incredible amount of analytical techniques, particularly nowadays, each with its pros and cons. So it's good to know what's what. And really, that sort of know-how has been packaged into this nested series of workflows called Chrono Tra. Hopefully, you've enjoyed some of these case studies that have tried to resolve multiple mineralization events in Tropicana, looking under stratigraphy in Mount Isa, and looking at some frontier exploration in East Greenland. And ultimately, we're here to try and reduce that exploration risk. That's all I've got, guys. Thank you.